Hi everyone, my name is Hyun-Suk Ha. I am a PhD candidate at the Seoul National University, South Korea. The paper I will be presenting today is titled Membership Privacy Preserving GAN. As described in the introduction section, membership inference reveals whether a particular data sample is involved in the target machine learning model training. Membership inference can be defined as a binary classification task that distinguishes whether the input sample is member or non-member. Membership inference has been widely studied in various applications, domains, and scenarios. It is well known that generative adversarial networks, GANs, are vulnerable to membership inference attacks, as the responses of the member and non-member samples from GANs are distinguishable. In this study, our goal is to train GAN, which is robust membership inference attacks. To achieve this goal, we aim to prevent the GAN from learning sample-specific features so that the responses of the member and non-member are indistinguishable. As described in the proposed method session, we propose a membership privacy preserving GAN. Membership privacy preserving GAN, MP-GAN, exploits a three-player adversarial game for membership privacy between components of the vanilla GAN and membership inference network, M. Membership inference network, M, inputs the responses of the data points from the GAN and determines whether the data point is member or non-member of the training dataset of the GAN. QX is the response from the internal activation of the discriminator. XRE is a reference dataset that is regarded as non-member dataset in the training phase of MP-GAN. If the three-player adversarial game for membership privacy reaches equilibrium, the responses from the training dataset and reference datasets are indistinguishable. Then, MP-GAN becomes robust to membership inference attacks. In the robustness to membership inference attack section, we visualized box plots for the two types of responses from the discriminator and generator of the GANs. Plots in the top row depict the validity score from the discriminator, and plots in the bottom row depict the distance between the query samples and its reconstructions, synthesized by generators. Blue boxes present the responses from the member samples, while orange boxes present the responses from the non-member samples. As shown in the plot, responses from the MP-GANs are less distinguishable than those of the vanilla GANs. Thus, the MP-GAN can provide a higher privacy level than the vanilla GAN. In the privacy utility trade-off to membership inference attack section, We measure the privacy utility traits of generative models as learning progresses. We evaluate the performance of membership influence attack models as metric for privacy. We use three types of membership influence attack methods depending on the type of responses used by attack models. And we evaluate the performance of downstream tasks as a metric for utility of the MPGAN. Downstream classifiers were trained on synthetic data samples generated by GANs, and they are tested by real samples. We compared two kinds of differential privacy GANs, differential privacy-based GANs, and two kinds of partition-based GANs that had been proposed for membership privacy. According to the experimental results, MPGAN provides high utility while maintaining high privacy level. In other words, MPGAN provides a better privacy utility trade-off than the others. In the sample-specific feature section, we visualize the reconstructions of training samples generated by the vanilla GAN, the MPGAN. MPGAN does not learn some detailed features such as glasses and wrinkles, while the vanilla GAN learns those features. This is because the three-player adversarial game for membership privacy prevents the MPGAN learning the sample-specific features of the training dataset. This mechanism contributes to MPGAN achieving a high privacy level. In summary, we have proposed the MPGAN, a novel defense against membership influence attacks. The MPGAN performs an additional min-max optimization adversarial game for membership privacy during the training phase to prevent it from overfitting the training samples. During the adversarial game for membership privacy, generator and discriminator of the GANs are trained to deceive the membership influence network M, whose goal is to determine whether the input data are sampled from, where the input data are sampled from. We have demonstrated that the MPGAN offers a better utility privacy trade-off than existing membership privacy defense techniques for GANs, even under advantageous scenarios for attackers. I'd like to thank our co-authors and sponsors. Thank you for listening.